This is the Pearson Edexcel AS Paper 1 Core Pure Maths. So it's based on this book here from 2019. It's 80 marks, it's 10 minutes longer than regular A-level Core Pure. Don't really know why. This is quite good practice though if you are doing regular A-level rather than just AS. Of course, if you're doing AS, this is the kind of paper you're going to take, but if you are doing regular A-level, this is also good practice, I think. Good, so singular matrices are matrices that have determinant 0, so non-singular means I'm looking for the determinant not to be 0. The determinant this is this times this, which is minus 28, minus this times this, which is plus 10, because there's two negatives there. And we get minus 18, which is not 0, so this is definitely not a singular matrix, it's non-singular, so that's good. Transformation of a plane is represented by this matrix here. So you've got a triangle R transformed by it. The area of the new triangle is 63. Find the area of the old triangle. Now, when you use matrices to transform shapes, like triangles, the determinant of the matrix is the scale factor. Specifically, actually, it's actually the determinant. Sorry, it's the modulus of the determinant that's the scale factor. So we can just do 63 divided by 18 to reverse the scale factor and get to 3.5. So in other words, 3.5 times 18 would be 63, so therefore 63 over 18 gives me a 3.5 of the original area. Good, and now show the line 2, y equals 2x. So if we take this matrix here and times it by a xy coordinate, but we'll times it by not the coordinate xy, but the coordinate x2x, because that's something that lies on y equals 2x, of course. What does that equal? Well, 4x minus 10x and then 2x minus 14x gives me this. And if I just factorize out a minus 6 from here, then we can see that this is still on the line y equals 2x. And so anything on the line with this transformation here stays on the line and therefore is invariant. Good. Question number 2, I think, is what we get to now. Good, so we've got roots alpha, beta, gamma, so we can use, I mean, there's two ways of doing this question. You can either immediately start using root stuff, so alpha, beta, gamma equals 12 over 2, actually, sorry, minus 12 over 2, and then like alpha plus beta plus gamma equals minus 6 over 2. That's actually not the way that I do these questions. It's just asking you for a new cubic equation that has these roots. All you really have to do here is just make the substitution w equals z plus 3, sorry, x plus 3. Rearrange that to be w minus 3 equals x. And then just shove that into there. And you've got a bit of expanding to do, but it's the safest way of getting these questions done, I think, because it's literally just expanding and simplifying, collecting, and you get an answer. Like I said, you could do some root stuff, and you could consider these roots and then expand this out and get the extra stuff in there. That's method number 2, but I think this is the method that I teach and that I would always just go with. I think it's much easier. Question number 3 then, so prove by induction. So as soon as you see this, that it's really tempting to do some partial fractions, but actually you don't need to if it's proved by induction. You can just start by saying, just let n equal 1, which means you're just doing the sum from 1 to 1, which is very boring. You just put in 1 here, and that's the only thing you add together. So put in 1 to this, and you just get 1. Put in 1 to that, and you get 3, which is 1/3, which is technically you could write as n, because n is 1, over 2 times 1 plus 1. So n equals 1 fits, this works, that's good. And now we're going to assume that it's true, that it works for n equal k, where k is an integer, so we'll assume if we put a k here, that equals k there and k there. And just assume that's true. And then we'll go for, and consider n equals k plus 1. And what happens here? Well, okay, let's put in k plus 1 into the top here, and consider this. Well, when we're doing sums like this, we could just sum from 1 to k, first, and then separately add in the last term of k plus 1. But of course, by assumption step, this is equal to this, so we'll shove that in. And here, this is literally, again, it's just a singular term, isn't it? So we just shove in k plus 1 into these two bits, and we get this. Okay, so now let's work with this then. So here, of course, we can simplify these two denominators to make this, I believe, on each one. And then now this has already got a 2k plus 1, so if we times this by 2k plus 3 over 2k plus 3, we can now combine these together. I've also expanded this out and then combine that in there. Now, of course, this very nicely factorizes in order to cancel with this, and we end up with this. And I think I can rewrite this as k plus 1 on top, obviously, over 2 lots of k plus 1 brackets plus 1, which is of the form this, where n has been replaced with k plus 1. So this has worked really well, and it works for k plus 1. So basically, if it ever works for n equals k, then it works for k plus 1, and we know it works for n equals 1 because we did that first, and so therefore it's true for all values of n, the integers. Good. Question number 4. So the first thing I always do, this Cartesian form of a line is, at least in A-level maths, almost never helpful in any case. So let's get that in vector form. So it's minus this, minus this, minus this, and that goes there, and then plus lambda this, 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 and that goes there. Cool. I think I then wrote out x as being, so the x term is minus 2 plus lambda, the y term is 5 minus lambda, the z term is 4 minus 3 lambda. So I wrote those out. And then this here, this r represents an x, y, z in column form. So that can be written like this, and then of course dot product, this is just x minus 2y plus z equals minus 7. And I can shove these three values to find the intersection of the line and the plane, if indeed it does exist. I can shove these values into there and just see what happens. And what we notice is that all the lambdas cancel, and the numbers over here are minus 8, and the numbers over here are minus 7, which obviously doesn't make sense, which means that these two things don't intersect. The line is parallel to the plane without intersecting it. So it's the third case there. So if you get a number here that's equal to the number here with no lambdas, then that means the line lives in the plane, and this thing would be equal to this thing regardless of what lambda is. Therefore, it's always in the plane. And if the lambdas don't all cancel, and you actually solve for a specific lambda, that means the line crosses the plane at some specific point. But we're in the last case here, and we're good there. Good. So a complex number question here. We've got three roots here, which are at minus 2, this and this, so that's these three roots here. Explain why they cannot all be roots of a quartic polynomial. Now, a quartic polynomial is a polynomial of degree 4. Now, the problem is that when you have complex numbers that are roots, of course, you've also got to have a root that is the complex conjugate. So if that's the root of a polynomial, minus 1 minus 2i must also be, and likewise, if this is minus 1 minus I must also be. But that would give us 5 roots, 1, 2, 3, 4, and 5. So that doesn't make any sense, right? So if all three of these are roots of a polynomial, then that polynomial is minimum degree 5. Good. This next bit then, which I believe is called a quintic, I think. Anyway, this next bit, so z1 minus z2, so work that out first, so I've done that there. That's z1 minus z2. That's z2 minus z1. z3 minus z1 is this. And now let's just divide those two things. Let's divide these, of course. Going to do a bit of realization here, and we get this. Just multiplying those things out, I think, which ends up being this, I believe. Yeah, and then, of course, to work out the argument of that, so that's the complex number that goes in here. To work out the argument of it, you just do tan inverse of this over this. But, of course, those two numbers are the same, so it's tan inverse of 1, which is, of course, pi over 4. And we're in this quadrant over here, so it is indeed pi over 4. Good. Excellent. Hence show this thing here. Now, what we need to say here is that when you're dividing two complex numbers, in this one and this one, the argument of that complex number, once you divide them, is the same as the argument of the first one minus the argument of the second one. So this is what I've written here, is that when you're dividing two complex numbers, we think of this as a single complex number here. The argument of those two numbers divided is just the argument of the first minus the argument of the second. So okay, but this we've just worked out as pi over 4. We can work out the argument of these two things very easily, right? Because that's tan inverse of 2 over 1 and tan inverse of 1 over 3. And we just immediately arrive at, they've written in terms of arctan, which I remembered to at the end, but we immediately arrive at what they wanted us to, which is good. Copy of figure 1, I think I moved on here, yeah. Copy of figure 1 labeled is here, good. Shade this thing here. Now, firstly, we need to write this in the form z minus something, so we'll do this. And likewise, this one, z minus something. And this is saying we want the distance from z to minus 2, which is what this means, the distance from some point z to minus 2, to be less than or equal to the distance from z to 1 plus I. So that's what that means in English. So 1 plus I is here and minus 2 is here, so those are useful. Obviously, like this point here is close to this one, so that would work, and so is like this point here. But this point would not work. And of course, the dividing line is a line that goes roughly through the middle like this. So what we can do is we can find the midpoint of this, which is clearly a half plus a half I believe. This is, by the way, just the third root. So that's the midpoint, a half plus a half I. Sorry, minus a half, I guess. Yeah, plus a half I. And actually, what we can also check out is this point here. Like, which side of the line is this point? Well, actually, this is 1 away this way, and then 2 this way. So that's 1 squared plus 2 squared is root 5 there. And then here, that's 1 down and 2 across. So that's also root 5 there. So this is actually equidistant, which means it's on the line that I'm trying to draw. So that gives me 2 points that I can draw from, and I'll get this line here. And I want to be on this side. I want to be closer to here. So it's just this shaded region there. And I think that's all I really need to do. Good. Question number 6. So this is a weird question. I don't like this question. I don't like this question. I don't like question 10, I think was the other one that I hated. But anyway, so we've got an arrangement of n marbles. We've got the first one is 10, the second one is then 13, then 16, and so on. And they're just verifying for us that the nth term of this is indeed 3r plus 7, which is fine. Show the mean mass is this thing here. So if we just add up a bunch of 3r plus 7s, r ranging from 1 to n, and then divide that by the number, which is n, we'll get the mean. So okay, let's do this. We can obviously separate like this. This, you should know, is n into n plus 1 over 2, and this is just n. We can obviously deal with this. We can put these things together, and then likewise, that's the total amount of weight, isn't it? So we have to divide, for the mean, we have to divide that by n, to then find this, which we can factorize our half from, and we'll get the mean they want us to get. Okay, now given there are 85 marbles, so we now know that n is 85, which is fine. It starts talking about standard deviation. So the first thing that I, of course, did was go to the formula book. Now, for people who don't perhaps know me too well, I hate stats with a passion. So I had to go to the formula book to look these up, because of course I don't know them. You can see me control effing stander to try and find these things, because I honestly didn't know what the formula was until I looked at this. And what I decided would be the easiest thing to do would be to use this SXX thing here in this form. I thought that would be easy. I know that X bar is the mean. I do remember that from like 12 years ago when I last did this. I remember the X bar is the mean, but the mean is just this. And actually with n equals 85, I can just work out the mean, because I can just shove 85 into there, so that's fine. So I can put that in there, and then that's SXX, and then I can say the standard deviation is just that over n rooted. So that all seems doable for me. So I thought I would just do that. So when you put in 85, you get the mean as 136. So that's what's given me this formula. So I've got x1 is just obviously 3r plus 7 as we had before. X bar is 136, and then I've just bracketed that with a square, and then gone from 1 to 85. So this will be SXX, and then once I work that out, I'll put it into this thing, and I should get my answer. And that's my plan. Of course, this simplifies. It's worth knowing at this point that you could just put this in a calculator, and because actually that's, I think, what you're trained to do in stats modules, though I've never taught them, so I wouldn't know. But the fact that it says use the standard summation formula, and the fact that this is worth 6 marks, suggests to me that if I were to do that, I probably wouldn't get all the marks. So let's actually use the formula by expanding this out. And this feels really pointless because, of course, I know I could just type this in and I don't really care what the answer is, so I don't really care about doing it properly. But we expand this out, we get this, we separate all those things out. We've already had that this is just 85 times 86 over 2, and this is just 85 because it's just n into n plus 1 over 2, and this is just n, where n is this. Now this result we can again look in the formula book for. It's this result here, so we shove that in as well. Just replacing all the n's with 85s. You type all of that in and you get this, and that's SXX. So then we put it into here, divide by 85, and root it, and we'll get our answer. Hated that question because why on earth are they asking me about standard deviation in a pure paper? There's a reason that I don't do with the stats papers. I'm annoyed that they ask me. And we're going on to question 7, which is much better immediately. So now we have 3 roots. We know that if we multiply the 3 roots together, we'll get this one over 1. We'll actually get negative that because there's 3 roots, of course. Now, that doesn't end up being that helpful, but what you could notice if you are really tricky is if you add all the roots together, you'll get negative this one over this, again, because there's individual roots, so it's negative. So it's negative 8, which is 8, over 1, which is still 8. And what's really good about that is that the betas cancel. So the sum of the roots is negative this over this, which is just 8. The betas cancel, and I can just solve this for alpha. Times everything by alpha, This is just a quadratic for me to solve. We get these two things here. So alpha could be this, or it could be negative this. Now, I'm just going to choose that alpha is the positive, and then I'm going to go even further and just choose that beta is the negative, because they haven't given me any relationship between these roots. They've just named them things. So I'm just allowed to choose that. And then I can find the third root by just putting alpha into here and putting my beta into there, and I'll find the third root. So I've just put my alpha that I've decided into here and the beta into there. This just cancels straight away, so I just get left with this, which I can, sorry, this bit doesn't cancel, does it, because it's negative, negative, but that's fine. Rationalize this, or realize it, I should say, and we'll get this, which eventually ends up being this, and then we can just put it together, and we get 4. So the third root is 4. And by the way, if you made the arbitrary decision to make this one like the other thing, then you would just do it backwards and you'd find beta is 4, and it's fine. So that's why it didn't matter which I chose. But those are the 3 roots, so that's cool. Hence find the value of p. There's loads of ways to do this, but the easiest way is just to take this root here and say, because it's a root, that means f of 4 is 0. That's the whole point of this. That's why it's a root. F of 4 is 0, so just shove 4 into here in terms of p, of course, and you can solve for p very quickly, and you'll have your answer. Question number 8 then, all about vectors. So there's a point on this line here, and then another point here. We want to find the vector equation line. That's very easy. You just take one of the points, doesn't matter which one. So I'll just take this one, and then you plus lambda of what you have to do to get from this point, the one you chose, to the other one. So plus 600, minus 100, and then plus 100. And we'll get this. There's lots of acceptable answers to that, because you could have picked either point to start with. You can also go in the other direction, because you can just, because you would just be saying lambda was like a negative lambda or whatever, so it's fine. You haven't defined what that is, so it's good. So you can choose whatever you want, but that will be the vector, one of the vector equations you could use. Okay, now what is this question about? Well, it's about a mountain which we're modeling as a plane, which seems seems ambitious to model the side of a mountain as a flat, uniform object, but that's okay. We'll do it anyway. And then we want to create an access way from the side of the mountain. So from a point on the plane, we want to get to this line PQ, the pipeline PQ. So we want to go from a point on this to the line PQ, and specifically we want to get from this point here. Now we don't know where this point is, but we do know it's on the plane, it's on the mountain, right? So we can just put this x, this y, and this z into here, and we'll find our k value, because this must lie on this plane here. We can very quickly get k as 200, so that's 1 mark for just forgetting that. And so what happens here is we have a point, which is this point here, and that's on the plane, which I can't bother to draw. We have a pipeline here, which is like this line here, and we want to make an access line that has the shortest distance from this point on the side of the mountain to the pipeline. Now that of course is going to make a right angle, because that's how shortest distances work, and we just need to find firstly this coordinate here where it meets the pipeline and this distance. Now finding this distance will be trivial if we just know the points, because we can just do Pythagoras. So let's focus on how to find this point here. Now it's a little bit complicated, this idea here. You have to go back to GCSE a little bit, because what you can say is they've defined before, they defined an origin point, right, which was the access point they currently have to get to the 2 points on the pipeline that they currently have. If you read the question before, they had this control center O. I'll just go back to it for a second. They had this control center O, which has 2 access points to the pipeline, which of the 2 points we talked about. And they're essentially, the idea here is they want to know whether it's worth building an access point from this point instead on the side of the mountain. So okay, we have O here, and what I want to plan to do is, can I find this vector? That's my plan. From M to what I've called X, which is this intersection. And from GCSE Maths, I think I can, because I can just go to O and then to X. So instead of just doing this, I can just do this, then this. That's how vectors work. So okay, to get from here to here, M to O, well that's just going backwards along this vector, right? So that's going to be just this vector with all negative signs. And then to get from O to X, well that's just the definition to get onto this line. So that's just this line here. Right, what this line essentially says is you go to this point first from O, you go to this point that we've already discussed on the line, and then you start traveling along this vector until you get to X with whatever lambda value that requires. So M to X is this thing here. Of course, I can bring everything together. It's just minus 100, minus 300, plus 600 lambda, which is this, and so on. And now this is the vector M to X, which I know, as I've said, is perpendicular to the line PQ. So this thing here, dot, this thing here, the direction of the line, must be 0. And now we're on the home straight here, because all we have to do is do this times this, plus this times this, plus this times this, and that all equals 0. The numbers are horrific, but that's okay. We'll eventually solve for lambda, and we'll get lambda as this. And we can take that lambda value, and we can put it back into the line to find O has magically moved to there. I don't know why that's happened. That is poor copy-pasting job from me, but that's okay. We can put lambda into there, and we can find this point is there. And then, of course, we can just do some very quick Pythagoras. 50 squared plus 125 squared plus 125 squared square rooted will give us the distance of this here. That should be on 125, shouldn't it? No, it shouldn't. It should be on 175. Of course it should. I'm just being an idiot. And that's the distance from here to here. Good. Okay, and now the last bit of the question is saying, okay, is it really worth building this tunnel then? Is that really worth it? What's the distance from O to P, and what's the distance from O to Q? Now, O is, of course, 0, 0, 0. So the distance to this is just 300 squared plus 400 squared plus 150 squared, which is that, and then likewise for here. And both of those things are significantly longer than this planned tunnel here. So it seems like it's probably worth it. And then state one limitation model. Well, of course, you can just say that modeling the side of a mountain as a uniform flat plane, probably pretty ridiculous. That's probably pretty dumb. So yeah, sure. Cool, and that's the entire question, I think. Let's go to question number 9. So we've got an f of x here, and we're doing a volume of revolution. Now it's interesting, we're doing it through theta radians. That hasn't printed very well. Through theta radians around the x-axis. So we're doing an integral of y squared dx, because it's around the x-axis, between those two points there. But we're not doing it 2 pi radians, we're just doing it theta radians. Now, if you do a regular total swivel of 2 pi radians, then you put a pi here. And if you do a swivel of theta radians, you put theta over 2 here, because, of course, 2 pi goes to theta. Sorry, 2 pi, a swivel of 2 pi just puts a pi here. So you always put half of what your rotation is. So theta over 2 goes here, and like I said here. So we need to work out y squared. Now, this is just y here. So what I decided to do was factorize out an x to the power third, and then I can just square this a bit easier, because this squares to make x to the 2/3, this squares to make something that's easier to square than I thought this was, so this just squares out to make this, I think. And then, of course, we can just expand back out again, and then we can shove this into here. And nothing really intelligent to do here. This goes to 5/3, and then you times by 3/5 is the way that I think about it, and this times by 3/5 is 12/5. And likewise for all of these, and then you just get a calculator and you put these two things in here, which gets you roughly this, and then you divide and you get this. If you keep ands in your calculator, you get a nice exact fraction as your answer, which is good. Cool. Excellent. Question number 10 then. It's a very, very long question about matrices. Let's have a look. So we've got some populations of juvenile chimps and adult chimps here, dictated by this matrix, and then this is the old population, this is a new population each year. Cool. Interpret the meaning of constant A. Now look at this very carefully. The new number of juvenile chimps is A lots of the old number plus this amount of the adults. So I think what's happening here is this proportion here tells us how many of the adults have made new young chimplings, or whatever they're called. Chimpanzee young. So that's that fraction, and then A amount of this must be the number of juveniles that are still juveniles next year, right? Because of course there's a point when they get older and become classed as adults. So this will be some number less than 1 to represent whatever proportion of juveniles stay juveniles each year from one year to the next. So that must be what that's representing. Anyway, at the start of the study, which is n is 0, the total number of chimpanzees is this. So J0 plus A0 is this, is what we can glean from that. And then after 1 year, J is this, so J1 is that, and A1 is that. Find in terms of A this. So actually all of this is pointless in terms of this. We can just define M to be this matrix and then invert it. So find the determinant, which is this times this minus this times this, and then swip these two over and then put these as negatives, and you get your inverse matrix. So that's 3 marks there, nice and easy. And then hence or otherwise find the value of A. Now this is a wild amount of work to do for 3 marks. But what you can do is you can front multiply this formula, or this kind of equation, by this, which will cancel out this one, and you'll just get this whole inverse matrix times these two equals just these two. So that's what I did there. And I substituted in the things that we have. So J0, A0, which I don't actually have, but I know what their sum is, which will be relevant later. And then J1, A1 here. And now I multiply this out. So this times this plus this times this can be my first bit. And then this times this plus this times this is my second bit. And then, of course, J0 is this times this, and A0 is this times that. But what's cool now is that I don't know J0 or A0, but I do know what they sum to. So if I add these two things together, I'm going to get this. And that's finally an equation in A that I can solve. The denominator is the same, so I'll just bring these together straight away. And then I'll just do a lot of regular math stuff, and you eventually get this. So A is 0.6. That's the most work I've ever done for 3 marks. But A is 0.6. That's fine. Calculate the change in juvenile chimps for the first year. So we just shoved A equals 6. We had a formula for juvenile chimps. It was this one. Yeah, does this here? Oh, sorry, at the start of the first year, yeah. I mean, that's J0, right? So we can just put A is 0.6 into there. So yeah, this formula here, and we'll get this number here. Good. Given the number of juvenile chimps is known to be decline, comment on the model. So our juvenile chimps are going up. So model not good. Study of population revealed the adult chimps stop producing after 40 years. Refine the system. I think you can basically only get the marks here if you've seen stuff like this before. What you need to do is you need to reclassify and recategorize an entire new chimp category of these chimps that are above 40 years old and can't reproduce. So I called them M for mature adults, the ones that are too old to now reproduce. And what you need to say is, okay, you've got juveniles who are too young to reproduce, you've got adults who are reproducing, and you've got mature adults who are not. So you've got these 3 categories now, and then you just have a 3 by 3 matrix times by your previous year's population. And now that gives you 1 mark. The only other thing you need to do is you need to put this information into this matrix. So the fact that the MN can't reproduce means when you find next year's juveniles, which is this number times this, plus this number times this, plus this number times this, you need to make this number 0, because that represents the fact that these things aren't reproducing here. And so the population of this is irrelevant to the next year's population of juveniles. Right? So remember, this number was telling you how many juveniles stay juveniles. This number was kind of the proportion of adults that have reproduced, and this number here must be 0 because it's independent of the number of matures. So this here will get you 2 marks for writing something like that. Anyway, thank you so much for watching, and I will see you next time.